Hey everyone. Yeah, super exciting today. I have with me Ratan from Succinct. Thanks for coming on.
Yeah, thank you for having me. It's a lot of fun. All of the whiteboarding sessions look very cool, so I'm glad to be able to talk a little bit more about blobstreamX today. It's gonna be fun.
Yeah, so today we're going to kind of go into blobstreamX, which is a product by Succinct. But then recently you guys actually came out with tendermintX, which is like almost like something sort of similar for
Mhm.
Cosmos. So maybe you'll have to touch on some, but before we kind of jump into how it actually works, what was sort of the problem statement that sort of got you here? Like when did you start it and what was sort of the motivation?
Yeah, definitely. I think there's a couple of areas which are interesting. So the first is a ZK Tendermint like client has always been something that people in Cosmos have been talking about, right? Like you want to have a secure way to bridge state from Cosmos chains to other environments, whether that's between Cosmos chains, from Cosmos to Ethereum. And so in the back of our minds, ZK Tendermint was always something that we were interested in doing. And so we were talking with the Celestia team, I believe about almost 8 months ago now, 8 months or 10 months ago. And one of the things that they were talking about was their blob stream bridge, which essentially allows them to stream blobs and data routes from Celestia to Ethereum because rollups that are dependent on Celestia for a DA but are settling on Ethereum need access to that DA. And the way that they do that would be via Blobstream. So how Blobstream originally worked was Celestia wanted to verify that the data that was posted to Celestia was actually valid in an Ethereum smart contract. To do that naively, you need to verify a bunch of EDDSA signatures. EDDSA signatures are the signature type that is signed by TenderMint validators, and TenderMint is the consensus algorithm that Celestia depends on. So you actually can't verify EDDSA signatures in Ethereum. It's really expensive. And with 150 validators, it's essentially something you can't do. And so what they originally decided was instead of doing EDDSA key pairs, we'll use ECDSA, which is the key pair that is supported by Ethereum and is the key pair that most Ethereum accounts have. So you can verify the signatures pretty cheaply in Ethereum. And so they were going to have each validator in their Cosmos chain have a corresponding ECDSA key pair, and then verify all of those signatures on Ethereum in a smart contract, such that you could actually verify that all the data routes that were being posted on Celestia could be reached via a rollup on Ethereum. Now, the issue with this design is one, you now have to have your validators maintain a separate key pair that's not the key pair they're signing for consensus, which is a custody issue, right? It's also like a coordination issue. Like, oh, like, is this something that's very sustainable? Additionally, in the future, let's say if Celestia wants to expand their validator set size, right now it's only about 150. You can imagine in the future, if you want to have a more decentralized chain, you'd want to expand that. Your cost to verify those signatures is going to scale linearly, which is not a nice property to have, right? Your gas costs are something you want to keep fairly constant over time, even as you upgrade your system. And so while we were talking to them, we recognized that one really cool thing that we could do is build out a ZK Tendermint client that verified the existing EDDSA key pairs without needing to have these validators maintain ECDSA keys. And additionally, as you scale the validator set, because you're just verifying a single ZK proof, the cost would stay the same. That was a bit of a long-winded explanation, but basically at a high level,
Not at all.
oh yeah, I feel like that was probably a little bit of a little bit a lot. So I think at a high level, essentially what we have is that you had these easy to say keys that Celestia validators are signing with that are expensive to verify in Ethereum. The original solution was to have each validator have an ECDSA key to sign with instead. That's complicated for a couple of reasons. Rather than doing that, we can verify all of the EDDSA signatures in a ZK proof and post that to Ethereum. And that is beneficial because you can now scale your number of validators on your chain without having to worry about increasing the costs of your bridge from your chain to Ethereum. So yeah, that's Blobstream came about, and we realized doing tendermintX was a subset of what we had to do for blobstreamX. So we're like, not only can we build out something that's really cool for Celestia with their blobstream bridge, but we can build out a product that actually all Cosmos chains can use if they want a bridge from their chain to Ethereum.
Okay, so it's relatively the same underneath the hood, whether it's blobstreamX or tendermintX. It's more just like what you're verifying, I guess you could say.
Or I'd say or if you look at the blobstreamX circuits, they actually call into the tendermintX circuits.
Okay.
So the blobstreamX circuits are a superset of what the tendermintX circuits do.
Okay. Yeah. Super helpful differentiator.
Yeah.
Yeah, I mean, to explain for people who like maybe super lost already. I'm with you, but I think like the bigger thing is, so like you have basically bridging. I guess the final goal for bridging is like you have like clients of every chain on every other chain, right? Like you basically are validating the signatures of the other chain on your own chain. So if you're over here on Ethereum and you want basically data bridged from Cosmos, ideally you would actually verify that this Cosmos chain is functioning as properly. Namely, what you're going to do here is verify the TenderMint consensus by, which is TenderMint consensus is what, just 2/3 of signatures here.
Yep.
And then you'll pass it over. The other piece about, and that's generally pretty easy, but then the harder piece, especially for like Blobstream, and we had talked with, whether it's Blobstream or, like I know like any sort of like client bridge, it's how do you maintain the validator set? So like, this validator set of say 150 people, that's not static over time. It sort of changes a whole lot, and having to pass over those validator set changes is often even a more difficult piece than just passing over the signed data from a static set. So, how do you guys go about handling any sort of validator set changes? What are sort of the limitations in the zero knowledge world that would kind of prevent, that would say maybe make a standard like client bridge a little bit better or worse?
Yeah, so I think at a high level, one thing that's really interesting about Tendermint consensus, and this is not something that's common with like Ethereum consensus or even like substrate consensus, is that you have instant finality, right? Like every single block, you have finality on Tendermint. So every single block, validators are committing to what the next validator's hash is. This is in contrast to Ethereum, where you have like an epoch, right? Same thing with substrate consensus. You typically have like epochs where the authority set is the same, and you essentially are going to verify in your like client, like, hey, this new block that I'm posting has this specific authority set. You're going to compare your authority, the hash of all of the validators in your validator set is equivalent to whatever you have stored in your Ethereum smart contract. But here with Tendermint, this is what we call the skipping verification circuit, which is a bit of a misnomer. But essentially what that is that you can actually prove or let me start a little bit more at a more clear level. So there's two different types of circuits in TenderMintX, which is what blobstreamX is built on top of. The first circuit is sequential verification, which is very straightforward. Sequential verification is when you're going from block I to block I plus 1. To go from block I to block I plus 1, you're going to verify that the next validator set hash, which is a part of the header in block I, is equivalent to the validator's hash that's in block I plus 1. So you're going to confirm that those validators hashes are linked. And you're also going to confirm that the previous block ID that is stored in the header of block I plus 1 is actually in that block I. And so sequential verification is very straightforward to understand. You're just confirming the two headers are linked. Now, you can imagine that this is pretty inefficient. You need to generate a proof for every single additional block that you're adding, right? Which can get a little bit expensive. One thing that's beautiful about Tendermint consensus is that because you have the property that every single block is final, you can actually skip a range of blocks. So as long as your validator set doesn't change too much between, let's say, block I and block I plus 1,000, there's a specific condition that you have where you can actually skip all of those blocks, as long as your validator set is like relatively unchanged below some bound. So
I think what Celestia uses, what, like 5%, I think,
or in TenderMint consensus, it's like something underneath, or like 1/3 of the stake weight of your new block needs to have been from.
I think that's block. Like the max. I think for safety reasons, like Celestia uses.
Oh,
like,
yeah, it's typically less. Yeah.
If it changes by more than 5%, you have to push over a change.
Yeah.
And then, but yeah, you're right. As far as like, it would be like, as long as it's within 1/3, you're safe.
Yep, exactly. Because in TenderMint consensus, 2/3 of the validators are signing off on every single block. Right. And if you don't have that, then you don't have finality. So like in Ethereum consensus, it doesn't halt, right? Like you have these properties where you're ensuring liveness, right? And that's one of the beneficial properties of having like non-instant finality. But in TenderMint, if 2/3 of the validators don't sign, your chain halts. Right. And one thing that's beneficial that you get out of that is that you can actually skip a bunch of blocks without ever having to maintain these validator set hashes on Ethereum. So that part is really cool for us because that means you're storing less data inside of your smart contract. It's cheaper to verify. You have to worry about less things inside of your circuit. So yeah, that's actually a cool property of tendermint consensus that's not common of other ZK Lite clients that we typically do.
So in your Lite client, what you would be verifying then is basically that would you be validating at each block that the validator set hash didn't change by too much?
Too much, exactly.
Yeah.
For that skipping verification circuit. Now, if let's say the validator set changes by a lot, then you need to do that sequential verification circuit. So if you look at the tendermintX circuits and the blobstreamX circuits, we actually have two different ones, one for sequential verification and one for the skipping verification where the validator set doesn't change too much.
Okay. And then, yes. So I guess if you're skipping blocks, you would verify, basically you would take the block at I and then the block at I plus 1,000, right?
Exactly.
And what exactly are you putting on there? So for like blobstreamX, like these are Celestia is storing on a whole bunch of these data routes that are, and then you're verifying it, and then you're just putting some Merkleized all of those data routes. Is that what?
Yeah, that's pretty close. So what I'm just describing before is just for tendermint, right? Like it doesn't include anything about the data routes that we're talking about in Celestia.
Well, I mean, for tendermint, it would just be what, like all of their block headers you're pushing over?
So in tendermint, we actually don't even have to, like in tendermint, once you've moved forward to a header, there's actually no reason for you to have all of the intermediate headers.
Okay.
So our tendermintX circuit is very lightweight in this way. It doesn't actually do anything with any of the intermediate headers because you don't actually need to do any computation for the intermediate headers on tendermint because you're essentially just skipping over all of them and verifying for this like future block, like, hey, the validator set hasn't changed too much, right? These validators, because it's still within the unbonding period, they can't have unbonded. And so if they do, let's say, try to submit a malicious header, they can be slashed, right? So when I say you can skip forward a bunch of blocks, you can skip forward within as long as it's less than the unbonding period for validators. For people that are unfamiliar with like the unbonding period, it's like how long it takes you to unbond in your Cosmos chain, whatever stake you have. And typically it's like 3 weeks.
Yep.
So like you could even skip forward like a whole week, right, of blocks. And you wouldn't have to do any computation over the intermediate blocks as long as your validator set hasn't changed too much. And the reason you can do this is you can make the assumption that like if the validators on the chain are malicious, they're trying to push a bad header to Ethereum so that they can like say take the money out of the Ethereum smart contract. Their Celestia stake or tendermint consensus chain stake could be slashed. So that's why the skipping verification works. But yeah, blockchain.
Let's say you were trying to build. Let's say you were trying to build like a bridge using the tendermintX.
Sure.
Thing. So you would push over. You would verify that like you would have some sort of bridge contract over on your Cosmos chain. Mm-hmm. You would want to verify a deposit. So the deposit gets sent over here, and then it gets pushed. You wait a few blocks. Somebody pushes it over. And then you would be able to, I guess, how would you go about in your ETH smart contract verifying like
proving that transaction
proving this
happened.
transfer happened.
So yeah, so essentially what you'd have is like, this is getting into the weeds of like the state containers in Tendermint, but what you can imagine is there's two different approaches. So like, let's say we have every 1,000 headers, we're posting an update to our Tendermint Lite client on Ethereum. You either could post a, like, there's a couple ways to do this, but you can essentially say like, hey, this transaction that I submitted at block 750, you can get to it from looking at the block at block 1000, either by going into like the historical state roots container, which is like what we have in Ethereum, or you could like prove the chain of headers back to block 750 and then prove your transaction from it. So like we have block 0 and block 1000, and you want to prove a transaction at block 750. You're either going to go in the state roots container like this and then go and prove your transaction, or what you can do is like you can prove the chain of headers all the way back to 750 and then prove your transaction. But either way, as long as you have a future header or block, you can always get back to those intermediate blocks that are within the range.
Right. Cool. Yeah, this was something, I was talking with some of the Blobstream people about it. It's always this, basically the more data you push across, then it becomes actually more expensive on ETH to like verify this thing and like more complex. And it's this like constant trade-off. Of course, who's paying the gas there. But yeah, no, that's good. Yeah. So because like, anyway, I'll let people look more into that if they want. We don't need to get into how Cosmos Merkleizes their
their state. That is a whole other rabbit hole. But we try to make it easy with tendermintX to do one of the hard parts, which is how do we verify all these signatures? How do we make it lightweight such that like people can extend it in the ways that they want to, right? Like, for example, some applications don't need you to post all of that data or don't need to have the functionality to prove that like this specific transaction happened at this specific time. They just want to prove like once per day, like, hey, the stake of these validators is this much on this chain. And so tendermintX is the most lightweight way that you can get that across using ZK. And then, that's basically tendermintX. blobstreamX we can dive into a little bit after. We were talking about this a little bit earlier, but how exactly, right, do you prove all those data routes that are happening at every single block between block 0 and block 1000? Do you do that approach I was talking about earlier where you go to every single header, prove that they were linked, extract the data root at every single header, combine them into a Merkle tree, and put the Merkle hash on chain? But yeah, that's essentially how that works. Is like we check the chain of headers that are within this entire range that we post, compute the Merkle hash of that Merkle tree of the data roots. We call this the data commitment on Celestia. And we post it on chain. So yeah.
Yeah, I mean, and then I'm guessing over here, is that on you guys, or do you guys like run an API then for people to get that proof?
Oh, exactly. Yeah. So like, or Celestia actually makes it very easy to do this. Like you can query for that proof. So like essentially like, are they currently working on this? You can essentially like look through all the events that are emitted in the smart contract. And from that, you can see like, oh, like what, let's say for example, that every 1000 blocks like in Tendermint, we're posting the data commitment, right? So like we post the data commitment for range 0 to 1000, range 1000 to 2000, etc. Now let's say, Nick, you're trying to prove block 7500. You need to know like, oh, what data commitment am I proving this against? Like what index am I in this data commitment tree? What is my Merkle branch to prove this against the data commitment root? So essentially what you're going to do is you're going to say, okay, I'm going to look in the blobstreamX smart contract for the events that are emitted for the data commitment ranges. I'm going to find what range I'm in. For you, it'd be 7,000 to 8,000. Then I'm going to request from either an API or some other service for all the data routes so that I can like reconstruct the tree, and then I can get my Merkle branch from that. Because getting the data routes is just querying a Celestia full node, right? Like any Celestia full node can tell you what the data root is for blocks 7,000 to 8,000. You can recompute the Merkle tree super fast, and then you have a Merkle branch. So anyone can run that service, super easy to set up. All you need is an ETH RPC URL and a Tendermint RPC URL. So yeah.
Yeah, no, the first time I dealt with that, I was using like the Polygon native data bridge. It was like similar.
Oh, wow.
As far as
how was that experience?
Well, I mean, like they're always like it's really important, I think, how people like I want to get back to people running full nodes because like when you're not running a full node, it's a super centralized process.
Yeah, of course.
You're
Yeah.
like, like all this stuff is like, oh, it's a completely decentralized bridge, except we have one centralized API that knows all of this. And
Yeah.
it's closed source. And we're like, all right, I guess that works, but we'll go with it.
Yeah. This is where Celestia is really nice. Is you have like 150 validators. Most of them have public endpoints you can query.
Yep.
So that part of it, or like Celestia has this page where they have like all these different like full nodes and consensus nodes that you can query. So I don't know. They made that process super easy compared to the experience in other chains. Like other chains, you kind of like are looking around, you see like maybe like public node will have an RPC endpoint, and then you'll go to like Alchemy and you'll like try to look for your chain. You're like, oh no, this chain's not here. You get an anchor, chain's not there, So yeah, I think the experience is a lot better. At least it has been pretty smooth for Celestia.
Yeah, well, I think Celestia, for the most part, they put such a high emphasis on running a node, which is
Exactly.
that it helps a lot.
Yeah.
Okay, so back to kind of proving and stuff like that. I guess the other thing, I think we have a decent idea about how the proof is working and what we're trying to do.
Mm-hmm.
What does it sort of look like in practice? So I'm over here on Ethereum, and
Yep.
I guess we'll just use Celestia as the example. My rollup just posted something on Celestia. I want it pushed over. Do I ask them for it? Do I ask you guys for it? Do I just do I go run this prover myself? What's going on?
So yeah, I think, well, short answer is you can do pretty much any of those.
Okay.
So at a high level, what's happening is that there's a regular cadence whenever blobstreamX will launch that proofs will be posted to Ethereum. I think this is still a little bit up in the air about what that frequency is. It'll probably depend on how often the rollups want it. But I think right now it's in the range of like anywhere from like once an hour to like once every 4 hours.
Okay.
And so what's going to happen there is like, those proofs are going to be generated probably by the Succinct platform, which is going to generate these proofs and post them. But let's say your rollup really needs this data root right now for like one reason or another. You can either request from a hosted endpoint for that proof to be generated, and that'll essentially be like, oh, like typically, let's say we're posting these data commitments every 1,000 blocks. Anyone can request a proof from this hosted endpoint for it to be done for a smaller range. Let's say like they want it from block 0 to block 250 instead of block 0 to block 1,000 because they really need to prove their data root at block 245 right now. That's one approach. So you can either use the data commit that's posted at a regular cadence by the hosted endpoint. You can request for a specific data commit range from the hosted endpoint, or you can locally generate the proof for blobstreamX, which is really nice because like, let's say that hosted endpoint goes down, right? Like likely won't happen, but if it does, you want to have resiliency so anyone can update that contract.
Celestia node. You gotta
exactly right. You want to run your own Celestia blobstreamX prover, right? Like one and the same. So you can download the circuits directly from the Succinct platform. You can format them in a specific way. We have instructions to do this that we'll be putting out with blobstreamX, and you can generate those proofs. So you just put in the target block you want to generate it for. The binary will generate the proof for you, and then we have a script to locally relay it to whatever blobstreamX contract you want to relay it to. So it's a very simple process, right? You have 3 different flows. Either you can prove that data root that you want to against the Ethereum smart contract following the data commits that are posted at regular cadence. You can request for a data commit to be posted early if once every 4 hours isn't fast enough for you. Or third, you can locally generate the proof and just push it yourself. Keep in mind, locally generating the proof typically will be less efficient, right? You're going to have to get a fairly large machine, right? Because these are pretty intensive proofs to generate. And it'll also be slower than generating it via the hosted endpoint because you're not going to be able to take advantage of the cluster proving that we have for some of these proofs. This is getting a bit in the weeds, but we have we call it map reduce when you're generating the data commitment. You're going to essentially parallelize the proving for computing the data commitment inside of the proof for Celestia. So locally proving, I'd say, is like the last resort, but we make it accessible so that anyone can prove it. And the blobstreamX system is resilient, even with failures from a hosted proving network.
Nice. So I mean, like, could I even run these things on my own Mac?
Yeah, Mac probably not. You probably need a little bit more of a larger machine.
Okay.
TendermintX you can run on your own Mac.
Okay.
I think it would probably take a while. Like we're talking on the order of like an hour or so, maybe longer, to generate some of these proofs on your Mac. Whereas on a larger machine, it might only take like 20 minutes or something, right? So, yeah.
Well, I mean, that's like I think this is the goal of what Succinct network, right? Gonna
Yep.
be without going, that'll be a whole different deep dive. We'll have to do.
Indeed, yeah.
But basically, there's going to be, what people see in the future is there's people with giant machines. You tell them you want this proof, and they do it for you really, really quickly and give it back.
Exactly. Like here right now, the hosted proving network has somewhat of a centralization vector, right? Like if that hosted proving endpoint goes down, run into issues. And this is an issue with a lot of existing ZK deployments today. Like ideally, you want a censorship resistant, decentralized system where you can generate and request proofs, right? Like then you'll no longer have to, download these proof generation binaries onto your machine, worry about setting up a large machine with enough RAM. You can instead just request for someone to do it. And whoever has the lowest energy cost around the world will generate it for you because they'll be able to generate a proof at the lowest cost. Like they'll typically be the one who will be able to generate that proof. And then that way, not only you're getting the best cost, but it's also typically being generated faster and posted quicker than it would if you were generating it locally. So, yeah.
Well, I mean, the only one I've actually done it for is like a tornado cache, which is really super
yeah
easy, and but even that'll take a few seconds on a Mac. So it's not crazy fast, and there's like nothing going on. So
I will say though, I also was learning how to build circuits originally, like on Circom, like via Xerox PARC. And it's so interesting how I think people associate, like these proving times are just getting so small for such complex proofs, right? Like now we can generate these like TenderMint proofs like super fast. Like you couldn't even do something like this in Circom. You couldn't even imagine of doing it. And that was only like 2 years ago, right? So I think if you wrote Tornado Cache, I'm not sure how true this is, but I think if you wrote Tornado Cache in like a more modern ZK library, the proving time would be like super fast, especially on client side. And that would be actually really interesting to try out. Obviously, US regulations and everything else. But I think like in the absence of that, it'd be really cool to see if like someone made like a modern Tornado Cache using like a modern proving system that was like hyper optimized for like super fast client proving. Maybe it would be even faster, like if there's good support.
You guys should have a contest. Like just like you can make the fastest Tornado Cache proof. And then
yeah, I think we might look into that. We'll see. US regulations and all, but yeah.
That's worth some points, I think. You can give out some. No, that's super cool. So then you would presumably have this, I guess, for Celestia, what sort of, obviously, like one of the bigger issues for any sort of TenderMint chain looking to use you guys is what's the bottleneck as far as limitations go? Obviously, if it takes 20 minutes on a computer to do a proving thing, you can only push it over every 20 minutes.
Yeah.
So like, what would be ways if a chain, say, wanted to use you guys, how would they sort of make it faster or come up with things like, or I guess the first question is, how fast is it for Celestia right now? Like, can you push it over?
I think, or it's bottlenecked more so on the cost on Ethereum, right? Like posting these proofs on Ethereum is just uber expensive, right? So like, let's say you were even able to get your proving time down, either via parallelizing it, putting it in a larger machine, whatever you want to call it. It's unclear to me if you would even want that, right? Like how often do rollups even need to check their DA, right? Like we're talking like on the order of like, maybe like once every couple hours, right? So on that side, I think cost in Ethereum is a prohibitive factor for even posting these proofs regularly. And I actually don't think it's something to optimize for. I think the better thing to optimize for is like ease of use, ease of deployment, and ease of like monitoring. Like, is this service up? Like, how easy is it to deploy? How easy is it to upgrade? And so I think, yeah, I don't know. There are many ways that you can look into like optimizing the proving time, but for something like a light client bridge, it's actually not as important for these kinds of applications for you to be proving it super regularly. If you were transferring tons of assets, then it would be interesting to look into, okay, like how can we, let's say, batch this ZK light client proof with a bunch of other chains, right? And like roll it into like one proof that can then be submitted. But in the absence of that, right, like Celestia has a very custom design for blobstreamX, right? Like you are posting this like proof that has, a very specific architecture. In the future, you could, of course, like compose this and aggregate this into like a single proof that could be posted on chain. A bunch of other people like want proofs posted on Ethereum at the same time. And that's likely what this trends to. So in the short term, I actually think it's probably suboptimal to like really optimize for like any specific application to be uber performant, because typically most applications don't need it posted that often. And until there's enough demand on Ethereum to like aggregate these proofs, no application will it make sense for you to be posting things regularly on mainnet Ethereum. Because like even for Celestia, I think committing a data commitment, like with including the cost of verifying a proof, is in the range of like 300 to 400K gas. And that is like $20 to $40, right? And if you're doing that once a minute, it's just going to blow your costs through the roof so fast, And most rollups don't even need that, right? Like how often are rollups even posting their data to Ethereum? Like you're talking like once every like couple minutes. And then like how often are you?
I think it's way
exactly
less. Yeah.
Yeah. So like ZK rollups are posting much less. Optimistic rollups are posting. I believe they post it fairly regularly, but like your fraud window is how large? Like you have like more than a day, 7 days, or even like an infinite amount of time, right, to post a fault proof. So I think, yeah, typically like posting quickly is not an issue.
Well, do you think people would like kind of like back to our example, like if we were to build a bridge using this, for a token bridge,
yep,
we would probably just do it optimistically, right? Like to save on gas. Like you would say, I'm just going to post it, and then if you don't like it, fund it with a bunch of gas, and we'll go get the zero knowledge proof, something like that.
Yeah, I think that kind of a design, there's definitely a lot of designs in bridging that can use this, where like you can use it as like a verification mechanism of like, oh yeah, like your bonded relayer posted the wrong header hash. They should be slashed. And like whoever posts the valid proof should get the funds from that slashing. And then there's another approach of like, it actually isn't that expensive if you're able to amortize the cost over like 20 different bridges, right?
Okay.
So I think either one of those approaches could be interesting, where like either you have like an optimistic approach, you can slash the operator whenever you see there's an invalid header posted using zero knowledge proof, or you can amortize the cost if there's enough demand for like 20 different bridges that are posting the same data. One thing that's interesting, though, that we're seeing is that this kind of like L1 thesis of many bridges interconnecting is kind of only being, I mean, you have like Solana, you have like a couple other chains. And I think within Cosmos, there's also a couple of interesting approaches where like, oh yeah, this is getting a bit in the weeds, but I think the L1 thesis, I think, is dying down a bit in favor of like this L2 thesis of like people want to continue, having their money held in rollups, whether it's like Base or Optimism or Arbitrum, and moving to L1 is becoming less favorable. But in an L1 dominated world, ZK light client bridges are a really effective thing. And that's where you can see that amortization coming from. So yeah, I think it's going to be interesting to see how it plays out. There's another team like in Cosmos called like Union, which is working on some interesting like bridging mechanisms too. Their approach, I'm not sure how much of it is public, but their approach wouldn't require you to be posting, 20 different Cosmos chain proofs and like aggregating them. Like instead, yeah, they have a slightly different approach to doing it, where like you would only actually need to post one proof to Ethereum. You wouldn't have to generate like 20 different TenderMintX proofs. You might only need to generate one. So yeah. Or I'm pretty sure that's public, but yeah. I hope I'm not exposing too
No, it's all good.
much.
We'll get them on a deep dive and we'll let them make
Indeed,
it good.
indeed.
Well, I mean, on that kind of L2 L1 thesis, the obvious question around some of this would go like, if I'm over here on ETH and doing this, is there any ability? How would you recommend that the Cosmos chain you're bridging over? What happens if they fork? Do they hold any sovereignty in a fork? Should you have an admin key or multi-sig over on ETH to basically be able to handle that? Does it just bust everything if you have sovereignty amongst these chains? So like if you're gonna have forks on the lesser chain, like if I want
Oh
to
yeah,
my validator set, could
yeah.
I do that? Do you add in some sort of time delay or dispute mechanism over on the ETH side?
Yeah, so like typically there's going to be a dispute mechanism on the tendermintX contract where if you're able to generate another valid proof for a different header hash, then the contract freezes. And then that's resolved by whoever is, like the guardian or the multisig that's like operated that is going to like resolve those disputes. So typically that would be some like set of distributed operators on that multisig, right? Whatever you want to call it.
Right.
They're like, oh, celestia chain forked. Like, let's figure out what happens. Now, keep in mind, if a tendermint chain forks, there's typically bigger issues that are going on than just your light client bridge, So I think that typically is the right approach is you make it permissionless for anyone to be able to freeze it once you're able to generate a valid proof. And typically what you'll see is with that multi-sig operator, they can typically detect when a fork happens and like preemptively freeze the contract, but they won't be able to have any other functionality than to freeze the contract in that case.
Yep. Yeah, because that's something like light client proofs are always great, except for do you just minimize sovereignty in some way?
Yeah.
So, but that said, I think it's always like you want to increase sovereignty, but then like at the same time you don't want to like increase multi-sig control over bridges.
Of course.
So it's this
I think
cool, yeah.
Yeah, I think the ideal medium is something in the range of like these multi-sigs can't post bad data, right? But they can prevent bad data from being posted. Okay. And I think that typically is the right approach. Is like if they notice a fork in the chain, let's pause, figure out what the new header you want to restart from is, confirm that there's social consensus on whatever new header hash you're starting this chain from, and then continue from there. I think that's typically the right approach is like, because, rollups can very easily verify from the fill nodes, hey, this is an invalid header hash you posted to the contract. Like we can no longer be dependent on this for our security. And that's one of the really nice things is when you're doing it on Ethereum, it's like, oh, easy to verify, we can hook this into our existing rollup contracts or whatever like full nodes are running for a rollup. We can query this data on the L1 and we can confirm it's correct by like checking its validity against like a Celestia full node. So yeah, I think those properties are pretty nice. But yeah, multi-sig should not be able to post bad data. I think that's typically the right approach. But I think being able to preemptively freeze in the case of, chains going rogue, I think is good.
That's okay.
Yeah. Or at least this is, not me speaking on behalf of this thing team. This is my personal opinion. So yeah.
It's okay. No, that's awesome. And then last, for people looking to kind of get more into the code, you had said that this is not Circom. Circom is outdated and juvenile. What's the new stuff that you guys are using? What should people be using for this?
Yeah, I think so. We originally, or for the past year, have been working on like a variety of different things to improve the developer experience within ZK. So we originally like launched telepathy, which was our proof of consensus bridge that validated the Ethereum sync committee. That was actually built in Circom. So like we saw very firsthand, like trying to take Circom to production, like how many issues there were. It's not something that's easy to use. It was what was the most battle tested at the time, which is what gave us good reason to use it as like, hey, like it's pretty well audited. We can trust the tooling stack. We quickly realized that like the pace of innovation in ZK is just getting so exponential, right? Like academics are pouring so much investment into it that like you're seeing these crazy advances in the proof systems. So what
we built blobstreamX on was Plonky 2. And we had built a library. Plonky 2 is a library that was put out by Polygon Zero that Daniel Lubrov, among other people, had worked on, where it essentially provides you a really nice framework for writing circuits in a more performant way. And they have like really nice properties, like there's powerful recursion, and your API for writing circuits is much better than it is in Circump. You can express like higher degree constraints, which is nice when you want to write more complex circuits. And now we're seeing that rather than writing circuits using these, we'll call it bespoke APIs, you can actually just take existing Rust code and write it directly instead of VMs. So like, let's say, for example, with tendermintX, instead of handwriting the circuit using Plonky 2, you can take existing Tendermint light client verification code, port it in Rust, and prove it directly instead of a ZK VM. So one thing we recently launched on Wednesday this week was SP1, which is our open source ZK VM. And with that, we actually saw that the performance of Tendermint inside of the ZK VM is getting really close to what the hand-rolled circuit looks like. And so I think when you look at that approach, no longer will you have to like verify these many different bespoke proving systems. Instead, you can just build using code that you've already written, Rust code for verifying Tendermint, put that inside of ZK VM, prove it, generate the proof, post that on chain. I think that's probably going to be the right approach. So I think it's going to be very cool to see how people will no longer have to worry about wrangling with circuits the way that people have over the past like 4 to 5 years. And instead, writing code will be the right approach. You just take existing code that's either been written by other people, port it into your ZK VM, or port new Rust code you write directly yourself into SP1 or another ZK VM, generate the proof, and run things like tendermintX. So yeah, I think that's probably going to be the approach that people will take. I think we're probably going to be taking blobstreamX to production with Plonky2x, which is the library that we wrote. But you can imagine in the future, once the performance of a ZK VM gets better via like community contributions, GPU acceleration, among other things, there could be some interesting things ahead. So
yeah, no, I'm waiting for, we can take all those old GPU miners and point them toward fun.
Yeah, we'll see. I don't know if we'll be able to change those, but I think definitely with there's just so much open source development around making ZK faster that I think it's going to, the developer experience as well as the efficiency of these circuits is just going to go through the roof. So
I thought like that's going to be such a good like narrative for you guys, for like if you could get like all the old proof of work miners on board and like you give them a job again and they'll love you guys. It's gonna be so cool.
Yeah, no, I think that'd be very cool. I do think though that'll probably be with new hardware. I don't think any of that old hardware is going to work, but I think there is always going to be demand for people that can run cheap hardware in areas with low energy costs, right? Like it doesn't make sense to necessarily be running stuff in even the US, right? You can imagine like a global proof network where like anyone can generate proofs wherever energy is the cheapest, right? Like at any given point in time, like the US is probably not the place where energy is going to be the cheapest in the world, right? Or even like Europe, for example. So you want to generate that in more globally distributed places. So,
I mean, people always said that though, but then like if you look at like where the proof of work miners were for these systems, it was like blue collar USA.
That is true.
Like these people running it was wild.
No, I do think you're probably right about that. But it's probably not, or it will be interesting to take it out of just the big data centers. I think that's where it's like, isn't that just so, it's so, I don't know, that part of it is so cool to me. Is like, you'll be able to run these light client bridges where like you request for a proof, someone generates it in like a country that's like in a different part of the world, and you're able to take that valid proof, put it on your smart contract in this like global, it's just, yeah, I think making the UX of that simple, making it straightforward to write in ZK, and just accelerating the efficiency of these open proving systems is going to be where we're going to see like a lot more applications come out. Like the onboarding curve into using ZK is still so hard, right? Like before ZK VMs, like
right,
it was just so difficult to even
understand or grasp like what is the computing paradigm that I'm doing and running these circuits. And it's very different than writing normal code, right? Like you have to express your problem as, this logic graph of you're like, okay, like how do we want to constrain this properly? There's many interesting nuances. You have to understand what the new proving systems are, right? Like you're hearing from your friends like, hey, Halo 2 is really good, Plonk 2 is really good. Like use it for this, use it for this. It's just a lot to understand. And I think that will be vastly simplified. And you're going to see a lot more applications using ZK as a result, because they'll be able to see like, hey, I'm doing something where ZK actually makes sense. And not only does it make sense, but it's easy to use. And that, I think, that easy to use gap is something that inherently feeds into the applications of it. So
yeah,
I think it'll be cool.
Yeah, I mean, on a more philosophical question on that, if you want to continue to pontificate with your own opinions, obviously, like we had talked about running your own full node, and there's the old idea of like Bitcoin, like don't trust, verify. As people start building these, like, do you see there be any sort of centralizing aspect to running these bigger and bigger hardware things? Like this is obviously the Ethereum thing. We want everyone to be able to validate on a home computer. And does this sort of fly in the face of that? And how are you guys thinking about keeping it small?
Yeah, I think we'll probably have, or the sync team will probably have some more thoughts on this we'll put out over the coming months. But like personally, I think that a lot of it comes down to how you design your system. Ethereum, for all of its faults, has tried to prioritize making it fairly straightforward to stake, right? With their chain design, with the node design, with the setup of the nodes, you see like people like Georgios from Paradigm working on making it super easy to launch, run, and maintain your own node. And I think in a similar way, prover networks probably have more centralizing effects than blockchains do, simply because your requirements are very dependent on the workloads that people are giving you. And also the need for decentralization is probably less strong than it is for an immutable ledger. However, if you want to maintain your censorship resistance properties, a lot of it comes down to how you design your mechanism for selecting who's going to be generating your proofs in the network. There are multiple different mechanisms that you can use for that. And I think a lot of it does actually come down to, how are you selecting the designated provers for your specific proofs? How are you designing your mechanism for rewarding those provers? Like, what is the way that you're guaranteeing like these different properties? And it's not just an issue of like, oh, largest person is going to win out and they're going to beat out everybody. There are ways that you can prevent that. And I think you can even see within blockchains that that's the case, right? Like there's so much effort from both engineers and researchers who are working on this problem of making it such that, the largest block builder doesn't just dominate all of the order flow and like take all the MEV, right? Like, you want to have ways to, or I think there's,
I'm joking.
How successful they are, I think that's a different question, but there is a lot of effort that goes into making that happen, right? You want to make sure that like, there's not these insane censorship effects that are happening at all the different layers of the stack. And in a similar way, because the properties of censorship resistance are important, we'll see it prioritized, improving networks that are designed the right way. So,
well, because I think it's funny, like always with, like if you look at Ethereum versus like some other chains, like the more decentralized the chain is, almost the harder it is to write a proper proving mechanism for it.
Yeah, no, I do agree that it is difficult, but at the same time, I don't know. I think there's a reason why it's designed in that way, and it's fine that the proofs are hard to generate, right? Like that's not what they're prioritizing for. Like being able to generate a proof for Ethereum, I'd rather have Ethereum be decentralized than have it be easy to be able to generate a proof for Ethereum. So, yeah.
All right. Well, this was super fun. What did I miss anything? Right.
No, I think at a high level we covered everything, and I think the code for blobstreamX and tendermintX is fairly well commented. There's good specifications for it. So if anyone that's watching wants to go ahead and take a look, feel free to look through the code. It's all open source, all MIT licensed. Feel free to fork it. If you want to extend it, you can go ahead and do that. And if you guys have any questions, my DMs at Ratan are always open, whether that's on Twitter or on GitHub. Feel free to leave an issue on any of the repos if things are hard to set up, hard to understand. And I'm pretty excited for these applications go to production, and it's going to be really cool to see how people continue to use ZK, whether that's via Plonky2x and more likely via SP1 in the future, to build really cool applications. Like even in the past, I think 2 days since we've launched, there's been so many cool open source PRs that people are making to SP1, and there's just this fanatic energy around it where like people want to make it as easy as possible to build a ZK, and they just want to collaborate with other people that are working just as hard to make it happen. And so yeah, I mean, if anyone else is interested, not only blobstreamX and tendermintX, but also interested in building on top of SP1, there's issues that we have in our repository that we love people to take on and try out, and we're happy to mentor people who want to learn how to build on top of ZK and make things easier, better, and more verifiable. So, yeah.
Super cool. Yeah. And what's your website for people?
You can check us out at succinct.xyz. And then on Twitter, I believe we're at Succinct Labs. So, yeah,
right.
All of our information is over there. But yeah, this has been a lot of fun. Thank you. Thank you for having me on. I appreciate it.
Yeah. Thank you so much.